Okay, this is the answer key to exercise set 1.2. We start off with the function j of x is 2/5 x squared plus 1 as shown on right. And we're looking for the area from -3 to 3 by calculating the sum of the areas of the rectangle. So this is a Riemann sum, because we are calculating the area of rectangles underneath the curve. And it's from -3 up to 3. So I only care about these rectangles, A, B, I'll label them A, B, C, D, E, and F. So reminder, the area of a rectangle is the base times the height. So looking at the base of all of these rectangles, notice that they're all 1, because we go -3 to -2, that's 1, 1, 1, 1, 1, 1. So I actually don't need to worry about the base because it's 1. So all I care about are the heights. Now, the heights you could get by kind of estimating the graph, but a better way is to plug in these x values, -3, -2, -1, and so on, into our function over here to find the exact height. So essentially what you're finding is you're adding the sum of f of -3 plus f of -2 plus f of -1 plus f of 0 plus f of 1 plus f of 2. Okay, so you're adding all those heights. That is like f of -3 is this value here. When I plug in -3 into the function, I will get f of -3. So what I'm going to do is plug these values into the function here. So -3, when I plug it in, I'm going to get 9, because -3 squared is 9, times 2/5, which is zero point 0.4, plus 1. So I will get 4.6. So I'll have 4.6. Then I'll have 2 squared plus, 2 squared times zero point 0.4 plus 1, 2.6. Then I'll have 1.4. Then I'll have 1. Then it's going to, since it's a parabola, it's symmetric on both sides, so it's going to repeat. Plus 1.4 plus 2.6. So altogether, when I add them all up, I'll get 1.4 plus 2.6 plus 2.6 plus 4.6. 13.6 units squared. Okay? So again, that's just the heights of all of these rectangles added together. And the heights I get by plugging in the x value at that point. Okay? So 13.6. Is it too high or too low? Well, visually looking at it, you can kind of see that the area above looks larger on the left sides than the area below on the on the right. And that has to do with the concavity of the slope. I'm going to show kind of an extreme version of that here. It's kind of like this. So basically the curve kind of comes inwards like this, like like that. So if you take a rectangle of that, this you can imagine, like, let's say, like kind of a square at one point. The area above here is greater than the area below because it's kind of pushing inwards, if that makes sense. So like if it was a straight line, they would be equal. This is equal, but since it's concave up, the slope is steepening as we go up. It's actually greater here than here. Okay, these would be equal. All right, so this is too high. All right, now I'm not gonna necessarily do this, but it says to sketch a function with 6 right endpoint triangles. What that's saying is in our function, our graph here, instead of taking the left value here, I'm going to take the right value. So I'm kind of going to overlay my new what my new rectangles will look. So instead of taking this value here, I'm going to take it at -2. So instead of -3, I'm plugging in -2. And here, instead of -2, I'm going to plug in -1. Essentially, you're shifting over one unit. Instead of here, it's going to be here. Instead of here, it's going to be here now. Instead of here, it's going to be the right side here. Instead of here, it's going to be the right side here. So essentially, everything gets shifted one to the right. So instead of taking f of -3, -2, -1, 0, 1, 2, you're doing f of -2 plus f of -1 plus f of 0 plus f of 1 plus f of 2 plus f of 3. But the thing is, because it's symmetric, and I'll plug these in. So that's 2.6 plus 1.4 plus 1 plus 1.4 plus 2.6 plus, because it's symmetric, f of -3 is the same as f of 3. So this is just another 4.6. They're the same thing. So right here, that's what it's talking about. It says you should have had the same answers. And that's because it's symmetric, because it's the same on both sides. That's why. Okay. It would be different. I mean, for example, it would be different if it wasn't symmetric. If it was just even if it was just a straight line, that wouldn't work. A straight line like this. If you're taking the left versus the right, if you're taking the left when it's decreasing, it's going to be overestimating. If you take the right side, it's going to be underestimating. I'll give you an example of the right side. Straight line. This time, take the right. It's going to look like this. This is just a rough sketch, right? You can see when you take the left, it overestimates. When you take the right, it underestimates. So these would be different. Okay. Domain and range. So this one, remember, domain is all the possible inputs. These are inputs. Remember, this is different. These are inputs, right? So what does not work? Well, here, if I ever divide by 0, it's not going to work. But the thing is, because I'm always squaring, no matter what I plug in here, it's never going to be 0. Because I'm always adding 1 and I'm always squaring, so it's always going to be a positive number. So this is everything from -infinity to infinity. Okay. This one, I can get 0 in the denominator, right? If I plug in a 0 here, it's not going to work. And if I plug in a -1 here, it's not going to work. So it's going to be, for this one, domain is everything from -infinity up until -1, and then a union. Zoom out here. And then everything from -1 to 0, and then a union, and then everything from 0 to infinity. Okay. So I'm accounting for those values. That's not going to work here at -1. It's not going to work at 0. Here, we have a square root. Now, the important things are we cannot square root a negative value, right? And we have a quadratic in here. So if you think visually, what this quadratic looks like, x squared minus 9, looks something like this. We have sort of this is -9 down here, and it's going up like this. So we cannot take the square root of any of these values down below. Where it's below the x-axis, I can't do that. So you got to figure out, when is this negative? When is it below the x-axis? And you do that by finding these zeros, and the area between is negative, right? So when is this 0? If we look at x squared minus 9, that factored out is x plus 3x minus 3. So it's 0 at x equals -3 and x equals 3. That's these points right here. This is 3 comma 0, and then -3 comma 0. Okay. So that means that my domain is good from -infinity up until -3, and then from 3 to infinity. Okay. So my domain for this one is -infinity up until 3, and it's going to be a bracket because 3 is okay, and then a union, or sorry, this would be negative 3, bracket 3 to infinity. Okay, that would be for h of x. Okay, these radical expressions, so we're converting from radical to exponents, and this is just following this pattern. You can see as an example, the formula looks something like this. Or the example, the algebra looks something like this: a over b equals the b root of x to the a. So in this case, this is the second root, right? So this is the same thing as k to the 7 over 2. This is the same as t to the 4 over 3. This is the same as n to the 4 over 2, which is just 4 divided by 2 is 2, so that's n to the second. And this one is b to the 31st over 5. Okay. Backside, analyze the graph. What does y approach as x goes to infinity? What does y approach as x goes to negative? So this is kind of an introduction to limits. As we go to infinity, y approaches infinity, right? So x goes to infinity, y goes to infinity. As x goes to negative infinity, y goes to negative infinity as well, because that's where it's going, right? As I go more left, more negative x, I'm going to get more negative y. It's just going to keep on going. What does y approach as x approaches negative 1? Sorry, x approaches 1 from the left. Well, it's approaching 3. So as x approaches 1 from the left, y approaches 3. As x approaches 1 from the right, come from the right here, y approaches 3. Okay. So we're going from interval to set notation. Essentially, this is x is greater than negative infinity, but less than 2, and x is greater than 2, but less than infinity. Okay, and then this one, similar, y is greater than negative infinity, but less than negative 1, and y is greater than negative 1, but less than infinity. What this could look like is it goes down to the left, but once you hit negative 1 and 2, there's a hole, and then it continues like that. That would be an example. Okay. Functions. So each one of the functions increasing, but increasing differently. We're matching the functions to the graphs. So first one's a straight line, meaning I should be seeing a consistent rate of change increase. So let's see if I can figure that out by looking. So 38 to 52, that's plus 14, plus 14, plus 14, plus 14. So this is plus 14 each time, it looks like. Plus 14, plus 14. Yeah, this continues plus 14, plus 14. Okay, so this is linear because constant rate of change plus 14, this has to be A. Okay, if we look at this one, just visually I can see the jumps are big at the beginning, like 20 to 40, and then later very small. This looks like it's increased. It's like 97 to 103, that's like 5 or so, 5.2. And then over here, it's nearly 20. So you're going from very steep to shallow. That is B. Because you're going steep, you're steep here, like this is steep, and then you're shallow. Okay, and then this is going to be C, because we're shallow beginning, and then we're steep. That's C. Okay.